So, Professor Caciolli has been conducting studies in field of nuclear astrophysics since 2007 as a member of a group of Luna collaboration. He has conducting a lot of study in also at ENFN Gran Sasso National Laboratory and at other major experimental facilities across Italy and Europe. He also serves as the coordinator of Luna Group at the University of Padua. In addition of these activities, he also is deeply committed to search outreach, in particular, including in this type of study also the outreach, including people with visual and hearing impairments. So today, this seminar titled Nuclear Astrophysics in Underground the Luna Experiments will guide through the question and the nuclear reaction as regard the evolution of the universe and the synthesis of elements in the universe, and also it will highlight the importance of conducting experiments in underground environment to achieve a height sensitive measurement, so free from radio from cosmic background noise. So we wish you an engaging seminar. Thank you.
Thank you. Good afternoon, everyone. Thank you very much, Livio. Thank you very much for this kind of introduction. I mean, luckily, I didn't put a summary of the talk because it was very clearly explained by this introduction. So I've seen that during this cycle of seminar, there are some other speakers that already discussed the nucleosynthesis in stellar environments. So I will try to briefly discuss this point. So why we are performing a nuclear physics experiment that involve reactions inside the stars or during the first minutes of the Big Bang nucleosynthesis. And then I will focus on some only some example of those possible reactions. So the one that can be studied, for example, in direct approaches by the Luna experiment, that I will use it as a case for discussing the importance of doing those type of measurements in an underground laboratory and how we can achieve good results thanks to this high sensitivity has been already discussed in the introduction. So nuclear astrophysics is something that connects a different field of the research, and this I find very nice because it's sort of interdisciplinary field of research that connects different expertise and sometimes also researchers that are doing, that are skilled in different ways that should interact together in order to comply a very challenging puzzle. So combining the information from observational astronomy, the cosmology parameters, the physics of neutrino that are involved in different possible ways in the so many stellar scenarios, and then everything is somehow driven by the stellar models with a lot of inputs, including the nuclear physics. So we are trying to understand the stellar evolution that could go in different ways, as it's depicted here. I will not enter in all the details, but at the end, in those many different scenarios, we could produce, not only we can power the energy of inside the stars, and so drive their evolution among the different phases, but also we will produce all the possible nuclides we can observe in the universe, on our Earth, and in our body through so many different processes. And it's important to somehow underline that all those different processes of course, not only in different scenarios, but also can be studied in a different way, only in different way with different experiments. Sometimes different techniques can approach the same type of reaction in order to be complementary and in order to give us better results. In other cases, we should design different experiments in order to focus on some of those particular processes. In particular, we can go inside the stellar core through stellar nucleosynthesis up to the iron, due to the fact that the binding energy is rising up to the iron peak. And then in order to produce all the other elements on the other side of this picture, so above the iron peak, we should go through S process or R process or other type. In this talk, I will focus on these, somehow small region where reactions between charged particles can occur. And also, I will focus on one type of possible experimental setup that can be used to study those processes, and in particular, in the field of the direct approaches. So even if we are focused on a small region in the chart of nuclei, there are so many reactions involved. Here you can see just another smaller part of the one before, involving the PP chain and the CNO cycle. So the two main mechanisms that are burning the hydrogen in our sun. And so also in this small part of the nuclei chart, you can see so many reactions. And this network of reactions can solve our puzzle in order to understand, for example, the number of neutrinos from the sun, or other important parameters inside our stellar core. And so, or for example, for some of those, in order to understand better the first minutes of the Big Bang. And so it's important to have reactions. In Luna, during the years, I've studied most of those errors, and also some other reactions involving the different other cycles of the hydrogen burning, and some important reactions involving the fusion of alpha particle with some isotopes important for the neutrons for this process. And now we are moving burning. But okay, just to remind you some important concepts that maybe are not, very well known by all the audience, despite I see many colleagues. So we are in the stellar models, we are interested in having the thermonuclear reaction rate that is driven by this quantity, so sigma V. And it's the rate of nuclear reaction, so the number of reactions per time and unit of volume. We should consider also that in not degenerate stellar plasma, the distribution of velocity or energy of our ions is described by the Maxwell-Boltzmann distribution. And so combining those two, we can obtain this equation for the thermonuclear reaction rate. Okay, here some numbers have been used. So here you obtain the thermonuclear reaction rate in this unit using the masses in this unit and the temperature in gigakelvin. Okay, so here you see that in this reaction, the reaction rate depends on the temperature, but it's an integral over the whole energy from 0 to infinite. And here you have the main parameter that is the goal of our experiments, the cross-section. So we are focused on obtaining this parameter that is a function of the energy, of course. If we consider and we focus on charged particle-induced reaction, we should consider that those ions are positive, and so before interacting and fusing together, they should pass the Coulomb barrier. And if we compare the energy, the maximum energy of the Maxwell-Boltzmann distribution that is given by KT, and so in the sun, for example, where we have a temperature of 15 million of Kelvin, the energy is about 1 keV. If we compare it with the Coulomb barrier, and here I put some example, energy is extreme. So those reactions can occur only by passing through the Coulomb barrier. So these depress a lot the cross sections. So those are very rare events. If we combine, so the cross section can be written in this way, where we have a function that is called astrophysical S factor that contains the nuclear terms of the cross section, and then an exponential terms that takes into account the penetrability of the Coulomb barrier. And so the cross section drops drastically with the energy. If we consider the Maxwell-Boltzmann distribution through the Coulomb barrier, we form this peak that is called Gamow peak. So we shift the energy window of interest for those type of reaction inside the stellar scenario at a given temperature to higher energy with respect to the peak of the Gamow of the Maxwell-Boltzmann distribution. And so in this energy region, we would have the cross-section. Move from the stars to the laboratory, and we try to determine, using some typical parameters of our experiments, so current milliampere, some density for the target, change a lot depending on the detectors, for example, and we look at different cases, you see that the rates are extremely low. In particular, here I put this table because you can see that, for example, some reactions that can occur in different, for example, the helium-3, helium-4 in the Big Bang nucleosynthesis will happen happened at 0.3 G. So the energy of interest is 160 kiloelectron-volt, and so we can expect 100 cups per our setup using some typical parameter. While if we go in the sun where the temperature is much lower, the Gamow peak will be at 23 kiloelectron-volt, and so the cross-section drops by so many orders of magnitude, and you are expecting, now I'm reading not so well, but 10 to the minus 7, yes. And this is important to be considered. So in many cases, we In some cases, it's affordable to measure directly in the gamma of peak. In other cases, we should measure as much as possible close to the gamma of peak and then do extrapolation, at least in the case of direct approaches, or combine direct approaches at higher measurements with indirect. Well, also who is not performing directly experiments in the Trojan horse that can over. So just to have a comparison of what is the shape of the cross section. This is the case of the carbon-12 alpha gamma. So here there is a plot of the cross section, and I point out that this is a logarithmic scale, and this is the correspective astrophysical S factor, where the tunnel penetrability is removed. So you see it's more evident all the due to resonances, and even, for example, is clear a structure due to a subthreshold resonance. So the S factor is also a very good way of underlying some nuclear physics aspects of our cross-section. So I will focus on this type of experiments where we have an accelerator that sends a beam on a target, and then there will be some detectors around in order to detect the products of our reaction. Okay, and in the laboratory we are reproducing exactly the reaction we would like to study, and that is important for the stars. Then, of course, we need a lot of manpower because those are very long time, beam time in order to pursue the whole experiment. The experimental requirements. For the accelerator, we need a very precise energy and very intense beam. As much as possible, somehow monochromatic, so with a very good energy resolution, because every uncertainty on the beam energy is propagated to the cross-section by this exponential 10. So, for example, if we have a 3 keV uncertainty at 100 keV, so a 3% error in the beam energy, and you put it into the formula of the cross-section, here there is this one because we can assume that is in this 3 keV the S factor would be constant. This propagates in a 40% error on the cross-section. Then this uncertainty the beam could be also due by the dishomogeneity in our target. So the beam passing through the target could change, and if we don't know exactly the target shape and the target profile, we could introduce some important systematics in our analysis. Then the reaction rate in the laboratory is, practically speaking, given by the cross-section, of course, of particles in the target, the number of particles in the beam, and then the efficiency of our setup. This is what we observe in our experiment. Beam we lose, so we can work on those parameters in order to increase the reaction rate. But the beam will lose energy into the target, and since the cross-section drops drastically with the energy, at a certain point you can increase the thickness of your target, but you don't gain so much in the expected yield. Then you can enhance and induce. Now we started working with accelerators of hundreds of microampere as a beam intensity. Now we are moving on the range of milliamp. But this introduces some problems in the reliability of target and their consumption. And then on the efficiency, 1 is the maximum. and usually don't reachable. I mean, always we are lower than this value. So that instead of working just on the signal, we should also work on the noise. And the noise can be, in this type of experiment, can be due by the interaction of beam on contaminants in our setup. And on that, we could study very well the setup material and all the surfaces, but then also by the environmental background. So that is due by cosmic rays, neutrons, and radioisotopes. This is a very important source of background and can be reduced in different ways, by active shielding, for example, but also by going in an underground lab. In particular, going in an underground lab, as you can see from this graph on the left, we have a strong reduction of the muon component, but also of the neutron component induced by muon interaction with the material of your setup. So, and you can see that, for example, the main laboratories for research in underground are at a level of thousands, 1.5, 2,000 of meters of rock above the experimental setups. And this brings to a reduction factor in the muon component by 6 orders of magnitude, and in the neutron component by more than 3 orders of magnitude. Then there are also some underground laboratories in the so-called shallow underground, where only 50 meters of rock are above the experimental setup, and here the reduction is about 99% of for the cosmic component. The effect of this shielding, here in this graph you see there is the meters of rock, the depth in meters of rock, or converted in meters water. And you know very well how important is to place something below also the water in order to reduce. That is a common way in order to compare different type of rocks and to put all the laboratories on the same graph. So in this way, we use the background related to the cosmic rays, so the neutrons and the muons component here. Then this part is dominated by the radioisotopes inside your experimental setup. And I will discuss that in a while. So based on this fact, the LUNA experiment was placed in the National Gran Sasso laboratories. That is nowadays the biggest laboratory in underground for the number of experiments inside. Here you have a map of the underground map. The laboratory is one of the 4 main laboratories of INFN. Here you see the laboratory on the surface with the Gran Sasso mountain. And here there is a map of the underground. We can enter by the highway, and the different accelerators used by the LUNA collaboration were here in one side corridor that has been installed in 2023 is in one of the main hall. Then the laboratory is mostly devoted to also other type of experiment, especially on dark matter and neutrino physics. So if we want also to reduce the radioactivity due to the radioisotopes, we should shield our setup by some passive shielding with very well selected materials. So copper, for example, 5 centimeters of copper is the usual, and then 25 centimeters of lead selected to be a lead with low radioactivity. We are not using the Roman lead that is used for some dark matter. Still, all the lead used in our setups is to be low in radioactivity. Then, since radon could enter everywhere, since it's a gas, usually above your shielding you put some, for example, a plexiglass box in an atmosphere pressured in an atmosphere of nitrogen. So to avoid the possibility of radon to enter inside the lead shielding. The effect is depicted here. So you see from the surface going in underground how much you can benefit. And here you have a comparison, for example, for a shallow underground with also an active veto, but even in this case, you don't reach the level of the Gran Sasso lab. In this lab, adding an active veto is still less effective, but is used, for example, for the very big experiment where the low counting is enhanced. Then, instead, having a lead shielding will provide a reduction by also 4 orders of magnitude compared to have without the lead shielding. I would point out that a lead shielding on surface does not have this effectiveness, because you see that the cosmic ray radiation will influence also at low energies. Without the lead shielding is not the dominant one, but with the lead shielding, it starts having an effect, limiting the effectiveness of your shielding. In fact, usually on surface, lead shieldings are have a maximum of 15 centimeters and not 5. And also there is a problem of muon interaction with your shielding that could introduce a new background signal in your detector. Also for the neutron detection, you can see that there is a huge impact. And in particular, we could also improve, there is a huge impact. Here you see a difference from surface and underground for two types of detectors, still helium counters, but with the counter made in aluminum or in steel. So going in underground, you start seeing the impurities of your detector, and so you can start to be sensitive to the selection of material. So, for example, here you see that the aluminum counter had a alpha decay impurities inside that limit the effectiveness of the Gran Sasso lab. So, based, Rods, of course. So, based on this, in one Nuclear in the Cosmos conference in 1990, somehow the father of modern nuclear astrophysics, and Gianni Fiorentini, that was the vice director at the time of Gran Sasso, met. Gianni Fiorentini was a neutrino theoretician, and so discussing among them, they proposed to install an accelerator in the underground laboratory. At that time, the director of the laboratory of Gran Sasso was Enrico Bellotti, and so they approved a letter of intent for a very small machine that was focused on studying few reactions of the PP chain in our sun. Maybe here you have a much bigger accelerators, and so these that we call accelerator is actually your source, because it was a duoplasmatron source able to provide 50 kilovolt maximum voltage. But with that setup, it was possible to measure in the gamma of peak some important reactions, in particular the helium-3 that was supposed at that time, before the proof of the oscillation, to be one possible solution of the neutrino missing neutrino problem. And so here you see a letter to the two spokesperson of the experiment at that time, Professor Corvisero and Rolls, by John Bacall, that wrote that this was a thrill that I had never believed possible. This measurement signal is the most important advance in nuclear astrophysics in 3 decades. So it was a very important result. Now we have in the Gran Sasso 2 working accelerator. One is a 400 kilovolt maximum accelerator with, you see, the typical parameter, so high intensity and very precise beam. And this was used to study, and is actually used to study mainly the hydrogen burning, but other processes can be studied with that. Measurements, and one devoted to solid target measurements. Then 5 megavolt accelerator, where we can also produce not only hydrogen and helium beams, but also carbon beams. So we can open the possibility to study helium burning and carbon burning. This is a facility of the accelerator named by the director Bellotti. And I mean, it was by myself and the Department of Physics in the University of Padua, also to produce an outreach project devoted to deaf and blind person that is called Stelle sulla Terra. So if you want, you can search our website and see what we have done. Okay, this is a movie of the internal part of those two, I mean, of the Gran Sasso lab and the two accelerators. That it lasts for 2 minutes. Unfortunately, due to the Teams connection, there is no the audio, but here you have see this is the lab outside, and this is the small accelerator. Here the first 50 kilovolt machine. This is the 400 kilovolt accelerator and the two beam lines. And here you see the a movie of the cross the site for the installation of the new accelerator. I would underline that the concrete shielding is has been mainly designed in order to avoid any interaction of our experimental research to the other activities in the lab, because as I already pointed out, the number of events expected with those accelerators is low. Okay, unfortunately, we don't have all the, so you see it's a new installed machine, so the number of stratification of cables is much less than in the Luna 400. Okay, we are not alone, and there are many other accelerators already installed or planned worldwide. Here you see our main colleague slash competitors, Caspar here in US, and Juna Jinping Underground Nuclear Astrophysics here in China. And then there is also the Shallow Underground Laboratory. We perform some measurements in order to study some ancillary aspects. So, for example, target study or some measurements at higher energies that does not require the underground, the deep underground, in order to combine the results and to improve the extrapolations. What? Tandem. Okay. It's a type of accelerator. So our accelerators are single-ended. So the source is inside, and you have only one step of acceleration. Okay. And usually the source for the single-ended is based on gases. So you start from a gas, and with the radio frequency, duoplasmatron, or different type of sources, you produce a positive charge ion, and you accelerate it. In a tandem, actually, in that tandem, you have also the source inside for a single step, or you have a source before, like the tandem here, that is much bigger. So you have the source outside, you produce a negative ion, then it's accelerated in one step. Then in the middle of the accelerator, you change the state of charge, and with the same potential, you accelerate a second time. At the end. And this is a tandem, so it can produce much higher energetic ion beams. Okay, I would use one case that we have recently studied in order to discuss the different requirements and the different aspects of our research. I would use the nitrogen 14 P gamma reaction, that is the slowest one of the CNO cycle. That is the picture here. You see here, in each of the CNO cycle, you have the conversion of 4 protons into an helium, and then all the other ions that are called catalysts after one cycle remain unchanged in their number. Here you have the first CNO cycle, that is the most important one, for example, in our sun, and the nitrogen 14 P gamma is the slowest one in this cycle. So it controls the velocity of that cycle. In this way, it controls also, for example, the number of neutrinos, the neutrino fluxes from the decay of oxygen 15 and nitrogen 13. This can be seen, for example, here in this table. Okay, on the left, we have a plot of the neutrino emitted by the sun. You have all the possible neutrinos from the pp chain, the beryllium 7, the boron 8, and also here in green, red, and blue, the neutrinos from the CNO. If you look at this table where there are the uncertainties on the calculation of the neutrino flux, you have that for each type of neutrinos, you have the possible source of uncertainties. Here, S is the S factor, and the numbers are the 2 ions involved. So the nitrogen 14 P gamma, hydrogen and nitrogen 14, is this one. And you see that then here you have opacity and diffusion. Here you see that it is the dominant source of uncertainty for the calculation of the neutrino fluxes from the sun for the CNO component. That has been recently measured by the Borexino experiment and will be the goal of different type of neutrino experiments that have been installed in these years and are starting running in the next years. So it's important to measure it. As I told you, in many cases, and for example, in these with direct approaches, we can only arrive at a certain energies, but to reach the gamma of peak, we should go through extrapolations. And there is some danger on extrapolations, also depending on the uncertainty that you require. I like a lot this plot, this picture made by Klaus Rolfs. Now, the requirement for the cross-section at the gamma of peak for the sun for this reaction is below 5% if you ask to the modelist. So let's see what we can do. The gamma of peak is here, okay? Here you have the level scheme of this reaction, nitrogen 14 P that produce oxygen 15 in an excited state or in between some excited states with the emission of different gamma rays populating many possible excited states of oxygen 15. So you have for each of these possible cascade a component of the S factor that are depicted here, and you see how much they are different in shape and behavior. Okay, if we focus on the two main components, for example, and we look at the data in literature and the possible extrapolation based on different experimental setup, we can see that the extrapolations does not differ on the resonance, but differ in the region between the resonance, the two resonances, or below the resonance at the smaller energy. Therefore, we would focus on those two energy regions in order to constrain better the extrapolations. And this can be done. So one is between 400 and 1 MeV, and this is the perfect energy for the Bellotti facility. And another one is in the region below 400 MeV, 400 keV, so is the perfect region for the Luna 400. At the Bellotti facility, we have used a setup like this one, so with 3 different germanium detectors that can be moved in different positions, keeping one of them fixed in order to have a reference. And to measure the angular distribution, that is important if you want to have a correct value of the total cross-section of angles in order to constrain very well the systematic due to the angular distribution. And here you see that we have used 2 different types of targets, one implanted and one produced with reactive sputtering. So with 2 different techniques, with also different enrichment, one enriched in nitrogen 14 and one with natural isotopic ratio, in order also to constrain better the systematics due to the target. You can see here that for each target there are 2 different scans performed with different irradiated before and after long irradiation, and you see how stable they are. So in our work it's very important to check the reliability and the durability of our experimental setup in all the possible parameters. On the Luna 400 experiment, instead, since the energy is much smaller and so the statistics expected is very low, we moved to a different type of detector, so a BGO, that we compare to the germanium as a worse resolution but much higher statistic. This is a segmented detector. So the setup, you see the beam arrive from the left, you have the target at the center of the BGO, and the BGO will almost cover the total solid angle. So you have a total efficiency up to 50 or 60%. Each target is water cooled, and then you have a copper pipe in order to remove the contaminants on the target surface and also to remove secondary electrons. Okay, so this BGO is segmented. So you can look at the signal of one crystal or combine with a coincidence the signal in all the detectors. Yes, all the crystals. So you see, if you have a cascade, if you look at one crystal, you see each gamma rays. If you look at the whole detector, you enhance the peak at the energy of the sum of the whole cascade. So in this way, we move the statistic to higher energies where the gamma spectrum is less affected by the background, and we compact all the statistics in one peak. Here you see, for example, for the study of the nitrogen 14P gamma, where we are expecting 3 different cascades, for example. Here you see in the so-called head-back spectrum, using the wall detector as a unique detector, this peak that is enhanced at the sum of the energy in each cascade, while if you look at the single crystal, you see all the possible peaks with their probability due to the branching ratios. The interesting thing is that we can go back in these, since we are using digitizers, we can reverse engineer this process. And so if I focus only on this peak, I can observe in the single spectrum what is produced only by the events that are forming this peak. In this way, I can obtain not only the removing all the possible other contaminants effect due to other region in the other back spectrum. And this has been done, and you see this is the black spectrum, but then if you perform a very constrained simulation, you can use this statistic in order to fit the experimental data with the different component of the spectrum. Each component is due to one cascade of those lines. Each contribution. In this way, we combine the high statistic of the BGO, so we can go at very low energies. But we can also obtain information of the different branchings, and then in this region. So this region. So this way, we are part with the Bellotti, this part with the Luna 400, and then, I mean, we are still for the Bellotti facility, the data have been analyzed in results, but probably, I hope that within this year, they will be published. Or at least submitted. You know, writing is always a long process, but waiting for the publication. For instead, the experiment in the Luna 400, the data taking has been finished, and we are analyzing the data in order to understand we could obtain all the branchings.
And this starts from the fact that basically, as you show at the beginning, the high energy of the gamma spectrum is well cleaned
Yes.
in the underground, while in the lower energies, you have gammas.
Yeah, actually,
could be.
Yeah, actually, in this energy range, there are intrinsic BGO, because it's bismuth, germanate, oxygen. So the bismuth component provide some contamination. Okay. See, yes, but see.
I imagine that there are some constraints. I mean, from the last simulation you show us this one.
Yes.
There are some constraints to give the exact how to say contribution of each transition there. No?
Yeah.
Yeah.
Can, I mean, of course, since we are close to this resonance, we can constrain all the simulations very precisely using the resonance that is that has been studied by so many experiments that now has a very small uncertainty, also in the branching cascade and their probability. And then having a very well fine-tuned simulation, we can move to lower energies where the branching parameters are not known. And for this reaction, we know that those are the branching component, the possible cascades and the possible cascades. Actually, this technique has been already published for the Neon 22 P gamma in the Ferraro paper of 2018, and then a long paper after describing the whole technique. So has been already tested with very good results. Okay. Just 2 slides to highlight that we didn't focus just only on the nitrogen 14 P gamma, but for the Luna 400 we have a lot of reactions, some completed, some understudying, and some started, and we are also writing a new letter of intent for the next future after 2025 and 2026, and then other probably 5 years. And then instead, for the Bellotti facility, we are running 2 very important projects. One is devoted to the study of this reaction. That is one of the reaction that produce the neutrons for the S process. So this is the Neon 22 alpha N, and will be studied with this array of liquid scintillators with the helium counter. So a new design detector for neutrons that has been founded by the ERC program with the PI Andreas Best. So it's an hybrid detector made of helium counter and liquid scintillators that should provide very high sensitivity to remove all the possible source of environmental neutrons, and also to avoid the problem of contaminant reactions. And this experiment is now on data taking. On the other beamline, we are focusing on the study of the carbon-12. Carbon-12, I probably should not enter in so many details because here has been studied very well, but is an important reaction because it determines the minimum mass for a star for ignite the carbon burnings, and then those stars can proceed up to core collapse supernova. So it's a very important reaction in order also to understand the number of objects we could observe in our universe and in our galaxy. This reaction has been studied by several experiments with a direct approach, and you see all the points. Recently, I mean, in 2018, there is these very beautiful results from the Trojan horse method performed by the group of ASFIN here. So you see, this is in black. Then there are some other reanalysis of their results proposing different normalization. And so we think, so it's important, this is the energy of interest, so the gamma of peak for this reaction. And so it's important, since they have seen a lot of structures, very interesting, not before suggested. Is important also with the direct approaches to be able to enter in this region. Up to now, as you can see, the data in literature for direct approaches are almost stopped at 2.5, maybe 2 MeV, but with huge error bars. So our aim is to enter into the gamma of peak to reach 2 MeV or even below with good uncertainties. Here you see the level scheme of this reaction. So for the particle we have the formation of the nuclei sodium-23 or neon-20 in an high energy state. Most of the decays arrive to the first excited states, so we are focusing on detecting those two gamma rays. We are also able to detect others, but it depends on the energy and the statistic. The setup we are planning is depicted here. So we will have a germanium detector, a very huge LED shielding, 12 tons of LED, and then the germanium detector will be combined by an array of 16 sodium iodide in a second phase. So we are buying those this year, and we will install them in the next year probably. The made in Legnaro. And here you can see some picture of the setup. So the beamline, the detector, the target, sorry, and the detector that is facing directly the target in order to maximize the efficiency, and then the LED shielding around. This is a picture, and actually this week, last week, we started the first carbon beam with the full setup mounted in order to start the data taking, while in December we tested the reliability and the stability of our target. So this is the Luna collaborations. That is a mainly Europe collaboration. UK, but of course we are not made just by university, but people. And so I will thank you and leave you with a sentence that I like a lot by Lawrence Krauss. Thank you very much.